Okay, we're still in chapter 11. We've been studying the chi-square test for goodness of fit. There are actually two other chi-square tests, and we're going to be uncovering both of those in this section. In this video, we're going to be focusing on the chi-square test for homogeneity. Just a quick brush up on the first section in this chapter. The chi-square goodness of fit test was really reserved for when we only had one population and we were trying to do some type of analysis on one categorical variable across that one population. For example, it might have been a stated color distribution that the Mars M&M company made about the percentages of each of the colors of their M&Ms, and the null hypothesis would be that their stated distribution for the one categorical variable of color across their one population plain M&M, say, is correct, versus the alternative would just simply be the stated distribution is then not correct. Our focus here today is going to be on a test called the chi-square test for homogeneity. And that prefix, homo, means same, which could help us a little bit here in trying to keep straight what the hypotheses are for this chi-square test for homogeneity. Okay, what you're essentially doing here with this test is you're still talking about one categorical variable, but now you're seeing if that one categorical variable is distributed the same over two different populations. So now we're talking about two populations, probably two samples, versus just one sample out of one population. The way that the hypotheses read, the null hypothesis is always that there is no difference in that distribution of whatever the categorical variable is for several populations or treatments. And then, of course, the alternative would be that there is a difference in that distribution across several populations, two or more, or treatments. Okay, you'll notice I'm saying or treatments. And when we talk about treatments, that's when we're talking about an experiment. So if you are reading through a problem and you notice this is definitely talking about assigning treatments randomly to groups, it will undoubtedly be the chi-square test for homogeneity. Now, this isn't always experiments, but if the problem is talking about an experiment, it will be the chi-square test for homogeneity. In the next video, we will talk about this last chi-square test, but for this video, we're just going to be focusing on the chi-square test for homogeneity alone here. Okay, so to kind of link together the main difference here between the chi-square goodness of fit test versus the chi-square test for homogeneity, the chi-square goodness of fit procedures really were just comparing the distribution of one categorical variable in one population to a claimed distribution, okay? But that didn't really allow us to compare the distribution of a categorical variable across multiple populations, and that is what the chi-square test for homogeneity allows us to do. So on the next page, we're going to kind of revisit something that we actually did, an example we did way back in chapter 1 when we started talking about categorical variables. We looked at an example like this that said, how old are individuals who play video games, gamers? It says the developers at Riot Games are interested in the age demographics for their popular computer game League of Legends, which we'll abbreviate LOL, and how it compares to its main competitor .A2. So they're going to take a random sample of 100 users from each game. So you can see here, they're taking a sample from each population. So we have the population of the .A users, and we have the population of the League of Legends. As soon as I see that we're drawing out two samples, one from each of two different populations, I should immediately think this is definitely going to be the chi-square test for homogeneity. Okay, now what we're analyzing here is we're analyzing one categorical variable across two populations, and that one categorical variable is the age. Okay, we're studying the age demographic here. I'll tell you another really giveaway here to using this chi-square test for homogeneity is almost always, if it's not an experiment, that would give it away. You can see the information is often presented in a two-way table, and that is a key indicator as well of using the chi-square test for homogeneity. Okay, so you want to be looking for that to help you distinguish between this test versus the chi-square goodness of fit test. And so what we did back in chapter 1 is we were asked to compare these age distributions. You can see they fall into 3 different age distributions: less than 25, between 25 and 40, and 41 or older. And we want to compare those 3 age distributions for each of the 2 gaming populations here, League of Legends and .A2. So let's compare using numerical descriptors and an appropriate graphical display. And so this is where we made things like a side-by-side bar chart. Now, if you're actually going to try to properly compare these 2 populations, you need to make sure that your y-axis is not the counts, it's not frequency, but it needs to be the relative frequency, which needs to be the percentages, because oftentimes your samples are not the same size from each population. Now, it just so happens in this example, we do have 100 in the sample for .A2. We also have 100 in the League of Legends sample. So it just so happens that those 2 samples were the same, but they don't have to be the same, and that's why we always want to try to convert things into percentages. So I'm going to go ahead and make a little legend over here. I'm going to just let a plain bar represent the age group less than 25. A bar with stripes in it will be between 25 and 40, and then a bar that's completely solid here will be those who are older than 41. Okay. I'm going to go ahead and label. It's important anytime we make any type of graph, display, bar graph, histogram, box plot, we always want to make sure the axes are labeled. Games, I will label here the game .A2, LOL for League of Legends. And then I'm going to go ahead and mark off some percentages here on my y-axis. I'm just going to go up to 50%. I think that's all the more that we would need here. Okay, this doesn't have to be exact, but I'm going to be putting, remember, these are percentages, not necessarily the counts here, although these will feel like they're one and the same because it was exactly 100 in our sample. I'm going to mark off those who are less than 25 from the .A2 group. There were 30 out of 100, so that is actually 30%. So I'm going to go up here. And I'm going to go ahead and mark 30% at the top of that bar. Okay, I'm going to go ahead and come across over here. These need to be all 3 of these age demographics for .A2. So I'm moving over here to 25-40 age category. 40 out of 100, that would be 40%. Okay, I'm going to label 40% at the top. This one gets the stripe. And then I'm at 30% again for those who are 41 and older. This one's going to get shaded in solid. Okay, I'm going to repeat that same thing over here for League of Legends. Looks like we are at the 50% mark all the way up here for those who are under 25, 30% for those in that middle age demographic, and down to 20% here for 41 and older. Okay, so this is accomplishing what they asked here, comparing the age distribution for each of these 2 gaming populations. Now, I'm just going to scroll back here because I want you to look at what the hypotheses look like when we're talking about this chi-square test for homogeneity. What we're trying to compare here is we want to say, is there no difference at all in how these ages are distributed across these 2 gaming populations versus the alternative suggesting that there actually is a difference in how the age is distributed across these 2 gaming populations. So that's kind of what we're comparing here. Okay, so let's go ahead and move on here to the next page where we can kind of dissect a little bit more here how to execute this chi-square test for homogeneity. I would like for you to go ahead and make this little note here right across from where it says chi-square test for homogeneity, is that it doesn't have to be an experiment, okay? It doesn't have to be an experiment. However, if it is, then this is the chi-square test that you should use. Okay, when we're done with this chapter, we will have uncovered 3 different chi-square tests. This is the one that, if it is an experiment, that you're going to use. Okay, once again, we are testing only one categorical variable, like age distribution, over 2 or more populations, like the 2 gaming populations, .A2 and League of Legends, or 2 treatments if we're dealing with an experiment. Okay, I think the key point here it mentions is you want to run this test when you essentially are taking two samples, and that's why a lot of times the information is presented in a two-way table, which is another kind of giveaway that this is the test you should use. Okay, our null hypothesis is suggesting, look, there is no difference between the true distribution of the variable across these several populations versus looking for convincing evidence in favor of the alternative hypothesis, which is that there is a difference in the true distribution of the variable across these several populations. Okay, the expected counts. Now you're going to see this is going to be a little bit different than what we're used to when we did the chi-square goodness of fit test, and this lends itself nicely into the idea that the information is often presented in that two-way table. I will go back and explain to you when we get to the problem how to come up with the expected counts for each cell in the two-way table, but it's essentially taking the row total for that particular cell times the column total, and then you're dividing by the grand total here. Okay, the test statistic for chi-squared is still the same. It's observed minus expected squared divided by the expected count, and we continue to add those all together, and collectively that summation creates our test statistic, the chi-squared test statistic. Okay, now the way that works, remember when we talked about this in the last section, we said this particular shape is always skewed to the right. Whenever we get that chi-squared test statistic, whatever it is, we'll just say right here is the value of chi-squared. Okay, what we're looking for is we're looking for all of the area to the right of that. That would give us whatever that area is, that is the p-value that we would use to compare to the alpha level to determine whether we would reject the null hypothesis or fail to reject it. Okay, in terms of degrees of freedom, again, this is a little bit unique with the chi-square test for homogeneity. The degrees of freedom is to take the number of columns minus 1 times the number of rows minus 1. That's kind of like each of the categories there. Again, we'll walk through that when we get to an actual example, and you can see what was mentioned right here is what I was trying to illustrate here in this graphic that I drew. The p-value is essentially the area to the right of the chi-squared test statistic. Okay, so let's go ahead and talk through what the conditions are for performing this chi-square test for homogeneity. You're going to notice a lot of these are familiar, but particularly when we studied in the last chapter, chapter 10, about comparing and drawing out two samples, one from each of two populations, we had this added fourth sort of condition we had to check, making sure that each of the two samples that we're drawing out are independent of one another. Okay, now I just would like for you to make this note to yourself here, that this independent, making sure that the samples are drawn out independent of one another and that they're not somehow mysteriously linked together, that one would influence what the other one was in any way. This is always a condition when there are two samples taken. Okay, and we experienced this again like in chapter 10 when we were drawing out two samples here. Okay, now the rest of these should look familiar. We need to make sure that the samples in and of themselves are taken randomly. Of course, the 10% condition right here applies when you are drawing out a sample. Okay, like in the League of Legends in the .A2 example, they sampled 100 users from each of those gaming populations. We need to make sure that the number in our sample times 10 is still less than or equal to the population size. Okay, the large counts condition here, this is a little bit different. All the expected counts need to be at least 5. I think we experienced that probably with the chi-square test for goodness of fit as well there. Okay, it needs to be at least 5. Now, I'm going to have you make one other note here of this list of 4. Since the 10% condition only applies to drawing samples, and the independence condition applies when you're taking samples, if the problem is dealing with an experiment, then those two conditions do not apply. So I'm going to say does not apply for experiments. Okay, does not apply for experiments. So if the problem is in fact an experiment, we would only need to state that the treatments were randomly assigned, and then we would need to show that all the expected counts are at least 5. Okay, so let's go ahead and try an example here. We're going to run a formal test here to see if this data provides convincing evidence at the alpha level of 0.05 that the true age distribution is different for these two games. Okay, so once again, you could flip back to the other page here to kind of see what these templates are for how to draft the hypotheses for this, but we're going to say there is no difference. Okay, the null hypothesis is always a statement of no difference. Remember, that always has the equal sign in there, implying there's no difference. So we say there is no difference in the age distribution for the game populations. Okay, and then the alternative hypothesis would merely be that there is a difference. And then you end it the same way. In the age distribution for the game populations. Okay, this is a good place here. We always try to include what the alpha level is. Just remember, if it's not stated for you in the problem, we often use just the default level 0.05. Okay, that brings us to the A in our Phantoms acronym where we're listing the assumptions. We also call those the conditions for the test. Now, this particular problem is not referencing this being an experiment. So we should have these 4 conditions we would need to list. I like to, when I list them, I like to kind of package together in one statement and say that both samples were taken randomly and independently of each other. That way we're kind of getting both this first condition and this last condition all in one statement. So I'm going to say both samples are random and independent of each other. Okay. And you could just make that statement unless you're given something in the problem that would lead you to believe that these samples were not taken independently of each other. You need to just at least include that in your sentence so that the graders know that you checked that off, and that is the assumption that you are working with when you're running this test, that they were in fact taken both randomly and independently of each other. Okay, the 10% condition. So we actually have 2 different samples, and we should be doing the 10% condition for each, but since the sample size was the same for each of these, I can kind of get away with only writing this once and say that 1,000 should be less than or equal to all the gamers for each population. Okay, I'd have to list that separately though if my sample sizes were different. Okay, then that brings us to the large counts condition. Large counts condition is where I need to show that all of the expected counts are greater than or equal to 5. Okay, now for me to be able to do this, I need to kind of construct a separate little, I'm going to construct a little matrix here, and I'm just going to label this as going to house my expected counts. Okay, so you can see up here, I'm going to go ahead and highlight. These are my 6 entries here. Those are all the observed counts, by the way. Okay, I'll just make a little note here. Those are the observed counts. Okay, what I highlighted there in that green. I'm going to be comparing those to the expected counts. There will be 6 of those down here. Now remember, back up at the top here, what the formula was for how to get the expected counts for each cell is to take the row total times the column total and divide that by the grand total. So I'm just going to walk you through a couple of those cells and then we'll fill them all in here together. Okay, so let's get the expected count for this spot right here. Those who are less than 25, age range for dot A2. I'm going to take the row total, which is 100, times the column total, which is 80, and I'm going to divide that by the grand total, which is 200. So essentially, on the calculator, and you don't need to show this work on your paper at all, or on the AP test for this, but this is what you'd be typing into the calculator. Now, if these are decimals, if it comes out as a decimal, you have to write down the decimal, do not round it. Okay, so then if I move over here to the next cell, okay, now I'm trying to find the expected count for the age range 25 to 40 for dot A2. I'm going to take the row total, which again is 100. I'm going to multiply that by the column total, which is now 70, and I'm dividing that by the grand total, which is 200. Okay, so if you follow that same pattern, move from one cell to the next, row total times column total divided by grand total, Do that one at a time. These are going to be your expected counts. And so I need to make a statement here for this condition that all of the expected counts, and I'm just going to list those because there's really only 3 types, 40, 35, and 25, are greater than or equal to 5. Okay, so that brings us down to the end step, which is where we are supposed to name this significance test. Okay, this is the chi-square test for homogeneity. Okay, chi-square test for homogeneity. And I'm going to, in the T step, calculate what the test statistic is. Now again, I'm going to scroll back up to the top, draw your attention here. The test statistic is to take the observed cell count minus the expected cell count, square it, divide by the expected. And then we kind of string those together. Okay, so for this, the observed would be 30 minus expected, that would be 40. So 30 minus 40, I'm going to square that and divide by the expected. Okay, I would work my way through here following that same pattern, dividing by what's expected. If you show the first couple of calculations, you don't have to write them all out. But if I did all of that, I would end up getting, for the value of chi-squared, to be 8.43. Okay, now I will show you how to do this on the calculator here in a moment. It requires us putting some things into matrices in order to be able to do this. For right now, this isn't too bad because you could just do that 6 different times on your calculator here. The chi-square test statistic is 8.43. Now we do have to report in this step the degrees of freedom. Again, up top here you can see the formula for the degrees of freedom is to take the number of columns minus 1. Well, I have 3 columns here, so it's going to be 3 minus 1 times the number of rows minus 1. I have 2 rows to this two-way table here. So 3 minus 1 times 2 minus 1 is essentially 2 times 1. My degrees of freedom is 2. Okay, now remember what we're essentially saying here is our chi-square test statistic is 8.43. I'm looking for the area to the right of that. If you go to your calculator where you find the normal CDF, press second and the vars button, you will notice, I believe it's option 8, you see an option for chi-squared CDF. Chi-squared CDF. Okay, it needs 3 inputs. The first input is actually your lower bound, which is the value of the chi-square test statistic. The upper bound, this is always a right-tailed test, so that'd be 10,000. And the last value is the degrees of freedom. If you type that in, you would get the p-value, the area under that curve, to be 0.015. 0.015 is the p-value. Okay, so we're going to look at that in order to make our decision. I'm going to kind of just move this down here. We're going to compare and say since p, 0.015, is less than alpha of 0.05, our decision is that we are going to reject the null hypothesis. And then our concluding statement is, since we rejected the null hypothesis, we have convincing evidence that, and remember, we just look back up and we essentially rewrite what our alternative hypothesis is, that there is a difference in the age distribution for the game populations. Okay, so that's how you run the chi-square test for homogeneity. Oftentimes, when you finish running these tests, you are often asked to do this follow-up analysis so that you can kind of determine which cell contributed the most, okay? Which cell contributed the most to your chi-square test statistics. So you can see over here to the side, I went ahead and already recopied. These are the observed values. These are the expected values that we came up with here, okay? And so when we do this, I'm just going to go ahead and fill in each piece of the chi-square test statistic. Now remember, it is observed minus expected squared divided by expected. Okay, so I'm just going to jot these in here real quick. If I went through and did each of these, okay, and then I'll also just fill in for you what each of these values end up being by themselves. This is basically what we did to get the value of chi-squared, that I don't remember what the exact value was there, but Okay, so what each of these come out as, this is 2.5, as is this. This is 0.71, so is that. And this came out to 1, and so did that. So you can see it kind of separates each of these so we can see how each one contributed. We can see which one contributed the most. Well, it feels like what contributed the most to the chi-square test value was this age group less than 20. So I'm going to say the age group less than 25 for both populations contributed the most to the chi-squared statistic. Now, sometimes it's good to then take it just one step further. You can see this is the dot A. Okay, this contributed the most. This is League of Legends. The expected, or I'm sorry, this is my observed counts. These are my expected here. Okay. You can see that what was observed was 30, but what was expected was 40. So for dot A2, that was 10 less than expected. And for League of Legends, here it was observed 50, but it was only expected to be 40. It was 10 more than expected. Okay, something I just want to draw your attention to, and then we're just going to peek at one other quick problem very quickly here. Remember the contrib list? It's found in second stat 7. That always like stored the values for like what each part, each cell was contributing. That only applies to the chi-square goodness of fit test. So that's why we kind of had to do this part here by hand and look at what each of the contributions were. That is only stored in that contrib list when you're doing the chi-square goodness of fit test on the calculator. Okay, so one last quick problem here that I kind of filled out most of the steps here for us. I wanted to look at a problem that actually was an experiment. It says market researchers suspect that background music can affect the mood and the buying behavior of customers. So they did a study in a supermarket. They compared 3, now look at this, here's the giveaway, randomly assigned treatments. Okay, you see them talk about treatments, you need to think, oh my goodness, we are dealing with an experiment. I know for sure I'm going to be using the chi-square test for homogeneity. Okay, they played no music in one supermarket, French accordion music in another, and Italian string music in the third. Under each condition, the researchers recorded the number of bottles of French, Italian, and other wine purchased. Here's the table that summarizes the treatments. Okay, so what we're looking at here is these 3 things right here. These are our treatments. And what type of wine they purchased is the response variable. That's the thing that's being measured. Okay, you'll notice the information is presented in a table, which is another little bit of a giveaway here. Okay, now because this is an experiment, I don't need to list all 4 of these conditions. I didn't draw a sample, so I'm not doing the 10% condition, and I don't need to check and make sure samples were independent if I didn't draw out a sample. So I only need to check that random condition and the large counts condition. The large counts condition is making sure that those expected cell counts are all greater than or equal to 5. We'll need to calculate that with this formula here in just a second. Okay, so here's how our hypotheses should read, that there is no difference between the distribution of wine purchased for each type of music versus that there is a difference between the distribution of wine purchased. Okay, we're going to just run this at an alpha level of 0.05, and we're going to go ahead and do our assumptions, our conditions. Don't need to do 10% condition, don't need to make a statement of independence. You can see I've listed the samples were taken randomly, but I need to make sure that I fill in what the expected counts are and state that they are all greater than or equal to 5. So once again, remember this formula right here is to take the row total, so I'm going to start right here with this cell right here, row total 99 times column total 84, divide that by the grand total 243. I do get a decimal, so I want to keep that decimal 34.22. Okay, then I'm going to move over here to this French section here. Row total times column total divided by grand total. Okay, that gives me the next expected count, 30.56. Okay, you kind of get the idea. I'm going to go ahead and fill in what all of these expected counts would be, and I'm watching to make sure that they are all at least 5 so that that large counts condition is being met. Okay, so I'm just going to say all expected counts are greater than or equal to 5. And if I've listed them here, that's good enough. I have it labeled here. These are my expected counts, so they can see that there. Okay, the name of this test, chi-square test for homogeneity. Okay, now I'm going to go ahead and list the first couple of values. Okay, observed minus expected squared divided by expected. Okay, I'm going to go ahead and do the next one, and then I'm just going to briefly explain to you how you can use your calculator to come up with this chi-square test statistic, because this has 9 different entries, so that's a lot to kind of type into the calculator. Okay, now I'm not going to be able to pull up a calculator here to show this to you, but I am going to talk you through how to do this. So if you have your calculator with you, it would be helpful if you could if you need to pause and sort of put the entries in, that's fine. You're going to be putting all of the observed counts into matrix A. So you're going to press the second button, and the matrix button is along the left side here. It's underneath the x to the -1 button. Okay, and you're going to go over to the edit screen, and you're going to select matrix A. The dimensions for matrix A should be a 2 by 3 matrix. I'm sorry, it should be a 3 by 3 matrix. Okay, you are going to, because you have 3 rows and you have 3 columns. So change the dimensions to 3 by 3. You need to move across the rows. Every time you hit enter, it'll bounce over. Go ahead and input all 3. These are the observed counts, should go into matrix A. Okay, you're going to put those in. If you need to pause, that's fine. Okay, then what you're going to do is you're going to go back into that matrix button again, bump over to edit one more time, come down to matrix B, and change the dimensions also to a 3 by 3 matrix, and move across and go ahead and enter in the 9 expected counts into matrix B. And again, if you need to pause the video to go ahead and put those in, you can do that. Okay, once those are all in, what you will then do next, now remember, we do have to report a few things. We have to say what the degrees of freedom is. Okay, that's the number of rows minus 1, well, that's 2, times the number of columns minus 1, that's also 2. Degrees of freedom would be 4. Okay, now you're going to go to that Stat Tests menu, and you're not going to see a test called chi-square test for homogeneity, but right above the chi-square goodness of fit test, you'll see a test called chi-squared test. That is the test you're going to run on your calculator for a homogeneity test. You're going to select that. It should by default say the observed are in matrix A, the expected are in matrix B. Go ahead and bounce down to calculate, and it is going to report to you probably the degrees of freedom as well as the p-value, okay, which is what we're really after. We want to know what that area is to the right of that chi-square test statistic. Also, it should report the chi-square test statistic as well. Okay, 18.28 is the chi-square test statistic, and 0.001, very small p-value here. Okay, so we should know what these conclusions are at this point. We're going to compare, since that p-value is very small compared to the alpha level. On this one, we are going to reject the null hypothesis and say that we have convincing evidence that, and we're stating our alternative hypothesis, you can see that right up here, that there is a difference between the distribution of wine purchased for each type of music. Okay, that's how you would run it on the calculator, and I would actually encourage you to use that feature where you're putting observed counts into matrix A and expected into matrix B. But do go ahead and write the first couple of entries here so the graders can see that you understand the formula. Okay, here's a few problems for you to go ahead and try that go along with this video.